The first task of the today binary trees days 2 is to create a binary tree using the letters of the word Harrisburg. I have an H. I have an A. I have an R. And I have an R. You notice my nodes have simply changed into a circular shape. I have an I. Actually, I have two I's. An S. A B. Get down on the same level. Try to keep my levels level. B, I, and R are on the same level. A U. Another R. And a G. One null, two nulls, three nulls, four nulls, 5, 6, 7, 8, 9, 10. I got 11. Unless I messed up.
I also got 11.
Okay,
No, I got 11 too. I just forgot to write one.
gotcha. How's that look written out as Harrisburg?
Funny.
Funny, it does. It does. All right, so let's talk a little bit about what we have. Let's start to get into some terminology. And, I'm looking at this guy. First thing I'm going to ask is, what's the root node? We'll identify it by the value there. The root node in this case is
H.
H. Okay. The letters that are in here, they're sometimes referred to as key fields. They're referred to as key fields. We have child nodes. Are there any that are not child nodes?
The root.
Yeah, the root. Good. Along with child nodes, we have leaf nodes. How many leaf nodes do we have? Take a guess.
2.
I'm going to go with the definition of a leaf node. And the one I know is it points to two nulls. It would be like the leaf at the end of a branch. So G, I, R, and U. 4 leaf nodes. G, I, R, U. Leaf node. Parent node. How many parent nodes are there?
6.
I hear 6. Shout them out to me. What do you have?
Or is it possibly 7? Does the root count as a parent node?
Does it have children?
Yes.
Yep. H. A has children. B has a child. R has a child. The second R has a child. And so does S. I came up with 6.
I double counted something.
Must have, yeah. The R's may have messed it up. Subtree. H has a left subtree. It's right there. ABG has a right subtree. All of that. So we can use subtrees. The height. What's the height of this?
Is it 5?
It is 5. It is 5. Sorry, you can't see some of that when I write it. It is 5. Where's my book? Keep going. Okay, so when are these trees used? Well, they're used a bit, and I'm just trying to stall because I have something and I can't find it, and I know it's like right in here somewhere. Ta-ta, ta-ta. When is this used? There used to be this little round blue toy that would ask questions, and then it could tell you what creature it is. And I think the first question was land or air. And if you picked land, it went here, and that determined the second question. If you picked air, it went here, and that determined the second question. And it was like, I can guess what creature you're thinking of within 10 guesses. Over here, it might say 2 feet or 4 feet, and then you'd go down. So we have these things called, where this is relevant, kind of, and it was in a decision tree. Same kind of idea as this binary tree. Okay, this one is set up for searching and that kinds of helps. Another example, I said, move, folder, get out the way, would be what's called a binary tree. And here's one that we're going to work with. Ta-ta. There's a binary tree. There's a binary tree from way back. We're going to get into some stuff like this that's actually really cool, in my opinion, when we start doing Huffman codes. But why do you think, okay, we have dots or dashes? Why do you think this was laid out the way it was laid out? Why is this first letter E? Why is this letter T?
Do the dots represent less than, and so therefore E is less than whatever your root node was, and dashes are greater than, so T is greater than your root node?
Here's I and A. Why would E be up here and not down here?
Is it one of the most commonly used letters?
Yeah. Yeah, letter frequencies.
Mhm.
So when you're sending message and E is a really popular letter, do you want E to be dot dot dash 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 dot?
No.
Right. You want that. And remember, I'm like, did we do this in 161? Yes, we did. Let me the summer's day, and we counted all the letters and we figured out what's the most frequent ones. We want to keep a message as short as possible. So the more common the letter, they came up with this for a certain reason. The more common the letter, the less dots and dashes it has. But here's a binary tree. It's broken down. We're going to do some really cool work with this. In my opinion, it's nerdy how you can create your own system where when I type in the message SOS, I'm doing dot, 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 pause, dash, 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 pause, dot, dot, dot. There's that S again. Well, what's between every letter is a pause, and that's like an extra character. We're going to do something where we can have immediate decodability without spaces, which again, that's going to be kind of cool that we're going to use less dots and dashes than you see here. And it's actually a lot of, again, I enjoy it quite a bit. Like, because I'm happy. So far, so good. Let's practice this one time. If I said, if I said infix, has anybody done yet? Infix.
Would that just be Harrisburg?
Uh, Harr. infix, prefix, postfix. One of them is going to give me alphabetical order. HABGIRRRSU. That one's going to be the infix. You want to practice one? Or are we good?
I'd like to practice one if we can.
You want to practice one? Pick it, pre or post.
Post.
Postfix.
Both.
Let's just do one. Postfix. Now, as soon as I see postfix, I'm going, oh crap. I need to just to be sure A plus B, and it's this, and then it comes after. So it's left, right, node. Oh yeah, that kind of makes sense. The only thing that moved was the node. Prefix was node left, right. Infix was left node right. Postfix left, right, node. So let's see if you can do a postfix traversal. Do, 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 do. Do, 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 do. And yeah, we're going to do that binary tree stuff. That's cool. At least to me.
So that code that you showed us, that binary tree, was that how they developed Morse code?
That was Morse code. Yes, that's how it came up. With dots and dashes based off of a binary tree. Postfix. Oompa loompa. Oompity doo. V. VBA. I. R. U. Then back up to the S. Then back up to the R. Then back up to the R. And back up to the H. I still think it was pretty cool when we did the Q and we did the push of the A, the push of the B. We got to an operator and went, okay, pop, pop, add, push. Isaiah, good?
Yep.
Yep. I appreciate you asking to see one. Questions? Okay. So now you might say to yourself, hey, self, we've learned about binary trees. Yeah. But whenever we learn about a new data type, we were looking at it as a linked list. And what's really nice is we already have that in binary tree spec file and implementation file, and it had a bunch of functions in it already. But why didn't we look at it as an array? Can I represent a binary tree as an array? And the answer is, drum roll, yes. Yes, we can. So let's take a simple binary tree. I'm giving you some letters M, P, E, C, U, P, O. Build that tree. Come here. Gotcha. Do, 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 do. Do, 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 do. I got an M. Woo! I can't find my red marker. There it is. I have a T. Woo! I have an E. And again, sometimes I draw squares, sometimes I draw the whole node, sometimes I just keep it simple. I have a C. Woo! I have a U. Woo! I have a P. Woo! And I have an O. What do you think? Pretty good? Oh boy, here we go. Sorry, I get excited. Sub-Zero. Sub 15. Sub-Zero, sub 15. Hmm. Get him! Get him! Get him! Where would you like me to put M in this array? Any thoughts?
Does it have anything to do with, like, specifically, can we put it based on I was thinking about, like, does it have anything to do with postfix or infix or prefix? Like, could we
Good
order it with that
thoughts.
in mind?
Good thoughts, but no.
Would you put it in the middle, like since it has like two subtrees?
Possible. Third option.
Just
Fourth option.
just at the start,
At the start. Yeah.
because we want
Yeah.
to work down it like we're taking the tree and turning it into a list.
Here's 0. M. Here's subscript 1. E. Subscript 2. P. 3. C. 4. We're going to leave blank. P. 6 is U. 0, 1, 2, 3, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Where does O belong? Where would O belong?
Is it 9?
I hear 9.
13.
I hear 13. This was null for 4. This was null. This was null. This would be null. This would be null. This would be null. This would be null. And so forth. 4, 5, 6, 7, 8, 9, 10, 11. So now the question is, Well, what do we do with this now that it's stored in an array? How can I work with it? How can I, question mark, how can I find a child? How can I find a parent? How can I find a child? How can I find a child? Well, let's take a look at n. M is at 0, and where's its children?
One and two.
1 and 2. Let's pick another one. P. P is at 2. Where are its children?
5 and 6.
5 and 6. Let's do one more. P. P is at 5. Its children are at 11 and 12. If I'm looking at N, where are my children? Where is my hairbrush?
Is it multiply? Is it 2n plus 1? And then it would be 2n plus 2 as well.
There you go. The children are found at 2. So if I went to 11, 0, and I said, where's its children? You're going to go 23 and 24. So even though we have an array representation, we still can do things just like we could in a linked list. But for this, we're bringing in our math background. So to find a child, it's going to be 2n plus 1 and 2n plus 2. So now you're still looking at this picture, but when you're doing some work and you want to find the child, whether to go left or right, where are they? You can find out where they are. Instead of a left pointer and a right pointer, we have to calculate the values. Find a child, find a parent.
I have a quick question.
Yes, sir.
Since 4 is null, how is it pointing to other two nulls?
It would just be that location. What's at that location? So now that brings up the question of what do we fill the array with before we start?
They're
This looks,
automatically filled with zeros, right?
I don't know. They're filled with something when we create the array. They're filled with characters. You may want to fill it with characters. If we are working with all caps, you may want to fill it with a lowercase n to signify null, like it's empty. It depends on how you would want to use it. And again, it's wide open. And again, it comes back to when I get two matching programs, the odds of them matching are 1 in a gazillion. And then, oh, I didn't cheat. Yeah, you did. Come on. You can fill it however you want. Nulls worked for us. I don't know what you want to put in here. Put in here whatever you want to put in there. The point is, we can represent a binary tree with an array. Which way do you think is the most preferable? A linked list or an array?
Linked list for sure.
Yeah, I think I would prefer a linked list as well. Okay, did we find the parent? Did we find the parent? 1, its parent is at 0. 2, parent is at 0. 7's parent is at 3. 8's parent is at 3.
It would just be the inverse of the child function. It would be child minus 1 if it's odd, or minus 2 if it's even, and then divided by 2.
You do it without odd and even. That's absolutely excellent. The wording and I've never heard it described that way, but it makes so much sense now that you say it. It's the inverse. How do you find the inverse? You switch the x and the y and then solve for the other one. And what did he do to solve? He said -1 divide everything by 2, -2 divide everything by 2. But we need it as a single. We don't want to check. If it's odd, do something. If it's even, do something. But you are really close with finding the inverse.
Make it an int and divide it by 2.
Do I have to make it an int? Is it already an int? N-1, integer division 2, chops off that remainder. 7 minus 1 is 6, integer division is 3. 8 minus 1 is 7, integer division is 3. Ching, 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 ching. Cool. We're learning a lot of good stuff in this class, let me tell you. Let me tell you, I like it. It's harder, but I like it. Let's come over here. Bada bing, bada boom. I'm in the NIOF book. I'm looking at page 656. 656. And we get our first definition. Our first definition is a complete tree. These three are complete trees. These are not complete trees. Without reading the definition, what is a complete tree?
It's a tree where um every parent node has like every node has its own child.
Not here. This has 2 children. This one doesn't have one. Good guess. Good try.
Is it the levels have to be even? And if not, then it has to fill in from the leftmost first.
Yeah, as your table grows, the way it ends up being laid out is it's filled and then left to right. So this is over here, these are over here, this is filled. This is called a complete tree. Each level of the tree is completely filled except possibly the bottom, and that has to be filled from left to right. These guys are not called complete trees. We're missing a node there. We're missing a node here. We're missing 2 of them here and here. So they're not complete trees. Now, something that we're going to use is a balanced tree. A balanced tree. Okay? Each tree node is going to be given a number. And balanced trees are going to come up, if not next week, the week after. And what a balanced tree is you take the left subtree and you subtract the right subtree. And what I mean by that is the height. The height. So if I come up here to this very first one, the left subtree is a 2. The right subtree is a 1. So this guy is 2 minus 1. Gives me a 1. This guy is a 1 minus 0, which gives me a 1. And so on and so on. So if I add these numbers and that differential is a -1, a 0, or a +1 for all of the elements, that's a balanced tree. Now later, we're going to do something where if I get something that's not one of those 3 numbers, 2, I'm going to do this Adelson-Belsky shift and recreate my tree so that it's balanced. Because once it's balanced, it's going to be quicker to search. This bad boy is really unbalanced. He is not going to be easy to search because worst case scenario is O. We're going to learn how to balance this as we go. The left subtree is size 2. There is no right subtree. So this is 2 minus 0. And that's telling me it is not a balanced tree. Now this guy, 1 minus 5, his factor is a minus 4. We don't want a balance factor of minus 4. Okay? And the definition is sitting over here. Here we talked about the height already, the number of levels in a tree. Questions? And there in the NIAF book, the NIAF book actually does a little bit of work with storing values in an array. Check that 0 out, all the way out there at 57. I bet you if the tree was more balanced, we'd use a lot less memory space. So all of these things are starting to tie together. Yes, it's a plan and it's coming together. All right, any questions? That's pretty much most of the talking today, the lecture. And we're now coming into what I'm going to have you work on to really crack your knuckles and get into dealing with an int binary tree, because we didn't really get to do much on Monday. So I would like you to add the following functions to the binary tree. Functions. One at a time. The first function would be count the number of nodes. So once this tree is filled, how would you be able to go through and get the number 1, 2, 3, 4, 5, 6, 7? How would you be able to get 7? Now, I bet you there's a recursive solution to that. I don't think I want to go. Maybe I want to go there. Maybe I don't. So it's a little thing, but how clever is your coding? So I can count the number of nodes. How would you count the number of leaves? What do we know by definition a leaf is? How many leaves are there here? Here's a leaf. Here's a leaf. Here's a leaf. C, O, and U are leaves. How are they determined to be leaves?
Because they point their children are both null.
They're both their children are null. Correct. Correct. And a third one, if you get to it. What's the tree height? What's the tree height? So all these things sound simple when I ask them. But now the exercise is, can I code these?